No.
Microbiome and
Nutrition and food science.
I beg your pardon. You say it again for me.
Nutrition and food science, actually.
Okay, nutrition and food science, yes. And but she's a mathematician, and so I think has that in common with all the speakers today. Has managed to bridge two very different fields. This is going to be a talk on something which sounds rather technical, and I'm hoping that we're going to understand something from it. So, if you're getting lost, would you mind if we interrupt you and ask for clarification?
You can ask. So, first I want to thank you for the opportunity you gave me to present some of my research interests here. So, I am going to focus today on some methods for statistical inverse problems. At the beginning, I'm going to give a short crash course in inverse problems, and after that I focus on some on Tikhonov regularization with balancing principle in Hilbert scales, and in the end some academic application are going to be presented. So inverse problems are a relatively big part of deterministic mathematics, and one of the most famous representatives of one of the most representative mathematicians is Tikhonov, and he defined an inverse problem as a methods which entails determining unknown causes based on observation of their effects. So this kind of inverse problems appear a lot in nanotechnology, in a lot of other, in medical imaging, and now in biology. And as an example, I can give you, for example, the interactions that occur during the ripening of smear cheese, or the effect of antibiotic on the intestinal microbiome from time series data. All this are modeled with the help of a Lotka Volterra linear system of equations, and they are actually they are estimating parameter of this linear system of equation, and this makes them inverse problems, and this is done in a statistical setting, so statistical inverse problem. Now, basic example of direct and inverse problem is integration and differentiation. So of course, when we are in school, we think about, we first learn about differentiation, and after that we go to integration, but actually the direct problem is going to be the integration. So for a function, a continuous function on 0, 1, we map this a into its integral on 0, again on 0, 1, and the inverse problem is actually the differentiation. So from a function in C1 on 0, 1, we want to compute its derivative. So it seems like a simple problem, but if you look at it as an operator equation and not in the right norms, then it becomes ill-posed. So why don't you take actually this stable operator between the set of continuous function and the set of C1 functions? Well, because if you have noise and you take the C1 norm, then you would need to know again the derivative of the noise, and this is something which you usually cannot get on. So instead of considering this norm on this in C1, you need to take the supremum norm, and in this case the problem becomes what is called in inverse problem ill-posed. This means the inverse of the operator f is not continuous. So we can illustrate this by taking again a very simple example, by taking some noisy data with a noise level delta and with some noise given by a sinusoid. Now, if you compute the error in the data, then this goes to 0 as the error level goes to 0, while in the solution, if you simply take the derivative here, then you get exactly the supremum norm n, and this goes to infinity. So this means that actually if you apply the direct inverse of the operators, then you get from noisy data a lot of noise in the solution, so much more noise than this delta. What are the steps which are usually taken in inverse problems? So the first step is to define a continuous operator which actually approximates the inverse. So in this case, we look at the very well-known central difference quotient, and this actually estimates the derivative here. This means the slope of this line, which defines the derivative in x, by the slope of this line, which represents the line which is going between x minus alpha u dagger of x minus alpha and x plus alpha and u dagger of x plus alpha. So this is defined in this way for the exact data u dagger, and of course we want to apply it again on the noisy data, and then we want actually to estimate the derivative of the function by this value. So the operator applied on the noisy data. Usually you work with on a grid and with a discrete grid, and so we assume that we have actually n noisy values of this noisy function u and delta. So let's see how does it work. Now, if we take exact data and alpha is the grid length is 0, 1, this works perfectly. Again, if we take exact data and alpha is 0, 0, 1, again this works perfectly. But what happens if we put only 1% noise level? Well, this is what you get if you actually use alpha as 0.1, and this is what you get if you use alpha as 0.01. So this means that it's not enough only to take the inverse of the operator, the continuous approximation of the inverse of the operator. You need to work something out with alpha.
So can you remind me what alpha?
Yeah. So it was actually the discretization, the grid length here, but usually this is called regularization parameter in inverse problems, but in this case, as I could actually directly define the inverse of the approximation, you can actually see it, what it has a meaning here. So now what we want is that this reconstruction error here goes to 0. And here we can use a very well-known trick. This means that we split the error in approximation error and in data error. This is similar to what we have in statistics as bias and variation. So it appears in non-parametric statistics also very often. And so approximation error, it goes to 0 as alpha goes to 0, but the data errors can be actually bounded by alpha, delta over alpha, and actually this goes to 0, goes to infinity as alpha goes to 0. So what we would like to have is actually to have a choice of the regularization parameter alpha depending on the noise level, such that this goes to 0 here to keep it going to 0, and also this term delta over alpha depending on delta again to go to 0. And so this R alpha together with this choice of the regularization parameter, it's called regularization method. Now another interest we have, it's the quality of this regularization measure, and this can be measured also by convergence rates. Usually they are available only when the smoothness of the of the A dagger of the exact data is known. So when we have some a priori information on a dagger, so I gave as an example here, if a dagger is instead of C2 function, then you can actually bound here in this way, and by choosing alpha as delta at 1/3, then you can really get here an order of delta at 2/3. So this means that in this case, with this choice of alpha and with this operator, we have convergence, and this is the rate is 2/3. Okay, now how do we relate this to statistics? Well, of course, one way to do this is by considering that the regression models. So this is a normal direct regression. This means that we have some noisy data of a function a dagger. Usually you have some design x1, xn, and some this can be stochastic or deterministic. We worked until now like with a deterministic design, and some error conditions, like this is centered, and the error should have second order degree moments, second order moment. Now for inverse regression, we do not have a dagger, we have actually a transformation of a dagger through this operator f, which we saw before, and additionally we have the noise, the stochastic noise here. So usually you consider f as a possibly nonlinear injective operator with discontinuous inverse in the sense which we saw before. This means this ill-posedness. And the aim is to actually to estimate this a dagger in a non-parametric class of functions. Now I took a generic name a hat. We see how we define it in our talk at least, and to study the quality of the estimator. Now I will make a short review. So what do we have to do? So we need to approximate the discontinuous operator by a family of continuous operators there alpha, then choose a parameter rule alpha depending on the data and on the noise level to obtain this estimate a hat. Then we need to see if this a hat is actually consistent in this sense. This means that the mean squared errors goes to 0 as the noise level goes to 0, and compute rates of convergence, and these are going to be helpful not only to see the quality, but as we will see before, also this can give us a smart parameter choice rule. So we are interested in the case that f is actually nonlinear. For this kind of problems, in 2004, Bissan, Sohag, and Moon proposed a two-step method due to the fact that usually it's very hard to estimate the noise level here, tau. And so in the first step, actually, he he chose an estimator. This means actually he solved a regression problem here. So he chose an estimator U hat such that this has a known rate of convergence, and this known rate of convergence is going to be actually used as a noise level. So this is how they solve the problem of the noise level. And the second part is the famous Tikhonov estimator of A. This means that actually you solve this penalized so this minimization problem, where we have here in the first term the distance between f of a and the estimator U hat, and the second is what we call penalized term, and this is this is what known in linear models in statistics as ridge regression. So actually what in deterministic inverse problem called penalization, what in deterministic inverse problem you call regularization, it's actually penalized estimator in statistics. So to get also rates of convergence here, there were one set of characterization of the solution here was used in their paper, and this actually is not enough, so you need more flexibility for smoothness conditions, and also there is a problem with this Tikhonov regularization. Actually it has saturation at 2/3, and so even if you get much more smoother data, then you cannot go beyond this 2/3. So that's why usually you can use what is called Hilbert scales to go over this 2/3. So a small history of the results regarding nonlinear statistical inverse problems. So the first was O'Sullivan 1990, first convergence rates results. Then Bissant, Hohage-Munk 2004, consistencies and optimal rates for one smoothness class, and then Hohage and Prikop, optimal rates in a range of smoothness classes in 2008, but for a priori choice of the regularization parameter, like we said, like we saw at the beginning of the talk. Now, how do you define this Hilbert scale? As a mathematician, you actually look at some unbounded self-adjoint strictly positive operator, and actually you consider the domain of the operator L at S, and with the S norm defined as here. But as non-mathematician, you can think about splines. So this means that these splines here, order 2, 3, and 4, give us different smoothness, and these are actually this can be considered in a kind of a Hilbert scale. Of course, the splines are actually approximated Sobolev spaces, which are actually the elements of the Hilbert scale, but graphically you can think about this kind of smoothness. Now, how can you get here from the 0 norm here to the S norm? So this means that actually A minus A0 should be smoother than 0 norm here. Well, we are going to see at the end of the talk that this is possible if you have some supplementary information on A, but not about smoothness. So this can be about some mean values or about some boundary conditions. So if you have some supplementary information on A, and you actually include it in your initial guess A0, then you can actually solve this optimization problem instead of the initial one, where here we had a 0 norm. So we have a stronger penalization term here. To get mathematically to get a solution, you need to have to fulfill some condition on F, and also on the derivative of Frechet derivative of F, because usually these kind of problems are used by linearization. Now, it's very important to have it's important for rates of convergence, at least, to have the knowledge about this so-called degree of ill-posedness. This actually tells us how much actually this Frechet derivative smoothes our solution. So we saw at the beginning that C was actually mapped in C1. So this was a smoother operator and a smoothing operator. So this is also in a more abstract way how this is going to be defined mathematically as in this Hilbert scale. So you need that this Hilbert scale can not only define our smoothness, our extra information on A, but also you would like to have also to get us the degree of ill-posedness. So under these conditions, actually you can go on and choose the regularization parameter. And in this case, you would like to use exactly the composition in data noise error and approximation error, which we saw at the beginning. So actually, the total error would look like this. This is a typical graphic of error for inverse problems, and you would like to have this alpha, but unfortunately it's very hard it's not possible to get that alpha. But what you can do is actually to take the approximation error, the data noise error, and to try to find this point here. Actually these are going to be also not exactly the errors, but also they are going to be their behavior is going to be estimated by some functions, as we'll see in the next slides. So this idea had actually Lepsky, and it was an adaptive choice of the regularization parameter for regression problems. So it appeared in statistics, and it was used for linear inverse problem by Matt and Perevezev in 2003 and 2006, in two papers. And so let's see how this error behave like. So now we see here the approximation error. It's actually alpha at the power q over 2 plus is, and data noise data error, it's a sum between some term here, delta alpha at the power minus p over 2 p plus s, and this term before. So actually what we had before, this was the behavior for the linear problems. It does not really, it's not exactly the same behavior as for our nonlinear inverse problems, but even in this case, you can take this non-decreasing function delta at alpha minus p over 2 plus s plus p, which does not require the knowledge of the smoothness of the solution, and you can actually use it to determine the right regularization parameter. So what is the idea behind this? Well, the idea is that you have you choose a sequence of possible regularization parameters, and you would like to determine the one which actually is gives the solution, I mean the AI, and also is the closest to the real solution. But this is also not possible. So what you get is actually an AI which is 3 times so you have a minimum radius here, which is possible between these sequences of parameters, and you want to have this this A dagger estimated by this AI. So in this case, you get order optimal rate of convergence, and in the stochastic case you get an order optimal up to a logarithmic picture. And as a very easy application, this parameter estimation as inverse problems, we can see here that the direct problem is actually to solve this boundary conditions problem, and here it's the inverse problem is actually to estimate the parameter a in given u delta. And so the condition which we need to fulfill, to know actually about the a dagger is the mean, and if you want to go on the scale, it would be all the odd derivatives of the boundary. So if this is known, then you can actually use the Hilbert scale to get a better rate of convergence for your.
Maria, I think we put it.
Okay, and I just wanted to say how this might look like. So this is how does it look? So this is the first part of the method where you can actually estimate u by local polynomial estimator, and here you have estimator of the of this parameter. So
thank you, Maria.
thank you for listening.
That's a different kind of talk than we've had so far. And I think it illustrates at least one thing of how much sort of mathematical thinking can be brought to problems which we might engage with. But so my question really is, in what way might this be relevant to the kinds of things that we're engaged with this workshop?
Well, as I said at the beginning, you can actually apply this for any kind of I mean, not only this method, but in general, methods for statistical inverse problems, for any kind of problems which require, for example, parameter estimation from a system of operation where this is actually ill-posed, and there are a lot. So as I said at the beginning, there were already some papers considering Lotka-Volterra systems of equation, and the estimator of these parameters actually are ill-posed problems, and they used already a kind of a Tikhonov there, but it was the model they used there, it was linear and it was very simple. So I think the more the complexity of the model increases, and considering also some nonlinear dependencies, then it's might be necessary to use this.
We have questions. Yeah. Oh, so David.
So a question and a comment. So the question first. So the adaptive regularization parameter technique that you detailed. So one disadvantage of that is that you have to redo the estimation at each one of the different regularization parameter values. Do you know if there are additional assumptions that you can make such that you can do more of a direct estimate of your regularization parameter alpha?
Well, usually, if you want to do it directly, but it's a trial and error thing, you take this a priori choice like the noise level, and at some power, if you have some information on the data, and you do trial and error until this works. But if you want to have something like which is mechanized, so you want to have a method which can work only to put the data and to get your result, you should be it's much better to do this, I think, at least.
Another talk. Last question.
Yeah, I think regularized methods like lasso or kernel ridge regression are well known in statistics. In fact, there are techniques which can give you directly regularized path of all the parameters in a very cheap manner. And basically, and the way how to estimate it is via V1 out cross validation or something like that, right?
Yeah, but this is for linear problems.
No, it also works for nonlinear problems. So, like kernel ridge regression?
Each of these methods also requires does something different. So, for example, this does smoothing, while lasso actually does model selection and also puts it chose another solution. So depending on what is your expectation on the solution, like for example, like in genetics, if you have actually high effects on few genes and zero in the rest, then you can use lasso. But if you assume that you have actually smaller effects and a lot, then lasso is not the best solution. For example, only to answer your question, each of these method has also its aim.
Okay, so with that, I think we better draw this session to a close. Thank you very much, Maria.